Okay, the first thing you want to do, always, always, always convert to moles. So I'm going to set up our titration over here, and this will turn into, water and good stuff. So it doesn't really matter. But what's important is over here on the left side. So we have, when you calculate the number of moles, you'll find it has 0.135 and 0.21 over here. You'll subtract the limiting reactant here. You'll end up with 0.075 moles of NaOH. And all you need to do is then find the molarity. So we'll do this over our total volume, okay? So we'll do 0.15 liters plus 0.35 liters. And then that will equal our concentration. So when we do that, I'll tell you the whole answer, but I'll tell you what the liters are. Plus 25, okay, 0.5. So this whole thing is just going to be 0.5. And when we divide it all up, the answer will be 0.15 molar. Okay, this is molar of NaOH, which is equivalent to the concentration of OH because it dissociates completely in solution. So we don't need to worry about any equilibrium constants, right? So we'll just do a negative log of this. And that will give us 0.82. So are we done? No. So this is the POH, right? Because we're dealing with base. So don't forget that. So I'm gonna take this over on the left-hand side. So we'll just do 14 minus 0.82. And that will give us a final answer of 13.18. Okay, any questions on this one? Okay. So for the next problem, okay, we're dealing with two acids here. We have our sulfurous acid and ascorbic acid. So this one will be SO4 with ascorbic acid, which is this one right here. Okay, so these are both weak acids, okay? They're both weak acids, and their Ka is, and Ka1, by the way, is the most important one. The other Kas are not that important when we're talking about major species. Regardless, if your Ka is less than 1, you're not going to, its product is not going to be a major species, right? So if the Ka is less than 1, which is the case for all weak acids and bases, then the starting material will stay in solution. It won't react more than, how to describe it? You won't see more products than reactants if the equilibrium constant is less than 1, because that's kind of what Ka means. It means like how much of your reactant is going to react and turn into product. And if it's less than 1, that means the majority is going to stay in the reactant side. So that's what we're going to see here. So we're going to see our sulfurous acid still in solution. Majority of it did not react because it has a Ka less than 1. We see ascorbic acid over here. That will also be a major species. Ka is less than 1. Water, always in solution. Always, always, always. And that will be it. That will be it for the answer. Any questions on this one? Okay.
How do you get H2SO3 again?
Yeah, so H2SO, oh, sorry, is that, sorry, I must have written that wrong. Okay, sorry about that. So sulfurous acid is just H2SO3, which is going to be a major species here. Ascorbic acid is this one. So both our initial acids are still going to be there, still around. And of course, we have water always in solution. Sorry, does that clarify things?
Yeah, thank you.
great. Okay. Jacob asks, when there is a salt, we include both the cation and anion. In what context do you mean? For major species? Well, it would be staying, it wouldn't, yes, okay, no, I understand, I understand your question, yeah, it would, you do include it, okay. And then Megan asks, do we only have to pick the stronger acid when we are doing ice tables? Yeah, so if you have a question like, find the pH of both of these acids together, you'll pick the one with the higher Ka value, because usually when you're given two acids, two weak acids, they're going to be so far apart in comparison of Kas. You might have have one a Ka of like e to the -4, and then another like e to the -10, and so like you're obviously like the 1 to the -10 powers is not going to have any influence on the pH basically. So yeah, hopefully that answers your question, Megan. I don't know if you'll expect another one of those questions on this quiz, but maybe yes, on the review, maybe. Okay. So what is the concentration of 3.45 molar compounds when it has been completely deprotonated? And you guys had more information. Sorry, this is my unedited version. You guys have the pKa's for this, okay? Okay, so your pKa's for this are going to be 2.2, 4.3, and then 9.7. You can do a lot. You can do a lot with these pKa's. What can you find with these pKa's? You can find the Ka's, okay? And then you can solve your titration, or not titration, your polyprotic problem. Okay, so I'm actually gonna make another page because this is kind of a lot of work. So okay, because we'll be doing 3 ice tables here. And I can show you shortcuts, but I want to show you the long way first. And you might have caught on to the shortcuts already. So basically, when it has been completely deprotonated here, I should have probably clarified this is triprotic. It has 3 3 places where it can be deprotonated. And so that's why it has 3 pKa's. And also 3 Ka values. Okay. So the first thing I would do in this problem, I would convert all of these. I would convert all of these to their Ka values. So this is going to be Ka1, Ka2, Ka3. And so all you need to do is put that number to the -10 power, because the way that we got from Ka to pKa, we did negative log. And so the way to get from pKa back to Ka, we'll just do 10 to the negative power of 2.2 to find Ka1. Okay. So now that we have our Ka values and our initial concentration, we can start the problem. So I'm just going to label this generic acid as H3A. Okay, we start out with our initial concentration. Oh, I have a question. Why do we have to convert? Why do we have to convert from pKa to Ka? Yeah, so this allows us to use the ice tables, right? Because now we're gonna go through 3 different ice tables, and we're looking for the concentration of the completely deprotonated form, which is A3-. Okay, hopefully that makes sense, Jacob. And you'll see it unravel as we continue. So it's not Ka1. So it's not Ka1, it's pKa1. So yeah, so this is the Ka that I found. You start off with the pKa. Sorry, this question is the unedited version. You had the edited version in the Google Doc where I listed the pKa. So these are all the pKa's here. and then I converted it to Ka. So we can use it in the ice tables. Hopefully that's clear. Okay. All right, let's start. So we have our initial concentration, 3.45. Okay. We have none of this. And we're just gonna, do our same old. And I'm gonna simplify it to this. We're gonna use Ka1 for the first ice table. So we'll do 6.3 e negative 3 equals x squared products. Products over reactants, so 3.45, and we'll solve for x here. Which is 0.147. Okay, now we're not going to get rid of this x value. We're going to use it. We're going to keep using it. So now in our next ice table, this will be the setup. That H3O plus never went away. We're going to add it right back. So it'll be right over here. That X value just went right over here, never went away. And then our H2A minus is going to be our reactant this time. And so I'm going to take that value, also X. I'm going to put it over here as well. Okay. And we have none of this conjugate base to start. Okay. So now I'm just going to do the same ice table. Same process. And then I'm going to simplify this value over here. I'm just going to simplify it using the 5% rule. You can always expect that. Again, I'm going to simplify it over here as well. Again, because of the 5% rule. All right. So now we're going to use Ka2, which is 5e negative 5. This will equal products over reactants, and you'll see what happens. This will happen pretty much every time that you'll do the second Ka table or the second ice table. We're going to be able to cross these off, right? They're the same value. We can cross them off. And so what you're going to see is the second Ka value is going to equal your second X value, right? So X will equal the Ka in only the second ice table. Okay, so what is X here? X here is going to be our concentration of Ha2 minus, which is going to be our new reactant. Okay, I'm going to drag down our H3O plus concentration that never went away. We have 0 to start there. And then for this concentration, we're going to use our new X value, which we just found, right? Because these are the same thing. We solved for X over here, which ended up being the second pKa. Sorry, I had some more questions. Wouldn't the second and third ice tables not really have an effect on the pH? Right. The first depronation and the first ice table will have the biggest effect. But this question is asking what is the concentration of this right here, the final concentration of A3 minus. And then in the third one, you still start out with H3O plus, which impacts the pH. Yeah. Yeah, I'm not sure what your question is there, Megan, but in the third one, you still start out with the H3O plus. Yeah, so we always drag that number down here because it doesn't go away. Okay, so let's put in our initial concentration here. 5e negative 5. And then again, same ice table process. We'll do minus X plus X plus X. This will simplify here. Okay, so now we're going to be using Ka3, which is 2e negative 10. This will be set equal again to products over reactants. So X times 0.147 over 5e negative 5. Okay, you're going to solve for x. Our x now is our answer, right? So we're looking for this. That is the answer to the question. The question was, what is the concentration of the fully deprotonated form, right? So then you'll solve for x just using algebra, and then you should get 6.8 e negative 14. Okay, long process, it's repetitive. Any questions here? And then I'll kind of like, I'll remind you what the shortcuts are. Okay, so the shortcuts for these problems, because they're the same process basically every time. So whenever you're given a question, you're looking for the completely deprotonated form, or sometimes they'll show you maybe like a picture of like the completely deprotonated form, and you're asked like, what is the concentration of this molecule? And you'll notice it's completely deprotonated, or it'll describe it or whatever it is. So you'll need to go through either the 3 ice tables. This definitely helps doing it all the way out. If you have time, this will be a little bit time sensitive quiz. And so the shortcuts that you can use, just please be careful. So no matter what, you're gonna have to do this process here. You're gonna have to do the first ice table. Oh, sorry about that. 1 second. Okay. No matter what, you're pretty much gonna have to do either the first ice table, or at least if you know just to do this. So this will be Ka1 equals x squared over the initial concentration. Okay, so you'll need to do this as like the first step here. Okay. Okay, first step is to find x1. I'm going to label x1. Okay, and that is the first step using Ka1, right? Finding x1. Just make sure you know like what you're finding. What does x equal? X here, x1 is equal to the H3O plus concentration and the H2A minus concentration, which is your new reactant here. Okay. The next thing you're going to realize, a shortcut, is when you solve for your x2, I'll label this x2, and you'll see this in my notes that I'll share with you that are from the review session. You remember my whole triprotic 3 ice tables work. You'll see I labeled them x1, x2, x3. So when you're solving here, this will be like x2. It's just like your next unknown value. This one will usually equal the Ka2, right? Because we're going to see that crossing off event, right? Where we have the same concentrations here. And so you can expect your x2 value, right, your unknown value, to equal Ka2. So you don't necessarily need to write all this out. If you remember that x2 will equal the pK or the Ka2. Okay, so that's that. That's your second ice table. Now we're going to your third ice table. Just recognize over here, we're still going to maintain x1, right? Because that concentration we found all the way in the beginning. And then this will be your x2 value. We just found it up here. Remember, it equals your Ka2 concentration. And basically what you'll find this setup. This will be your third step, I guess. So you'll do Ka3 equals your x3, right? This is your final unknown variable, x3, times your H3O plus concentration, or x1, right? Over this one, which is x2. So you're going to kind of see this pattern all the time. Just be careful that you know like what these numbers are, where they're coming from. But this is the pattern if you want to use it. And then you can solve for, this is x3 is your final value. Sometimes it might ask you what is the final pH at that point. And let me think. It might ask you like what is, because basically like you can find the pH from the first ice table because, right, this H3O plus concentration is not really affected by the second and third ice tables. Sometimes, like, I'm trying to think, like, maybe you guys can like let me know if you've seen questions with triprotic acids or diprotic acids, and it asks you something different than what I've talked about, and then I can let you know what to do in those situations. Anyway, so this was number 3. The answer was over here. Any questions on this or similar problems before I move on? I know it's a long process. Just make time for it on the quiz. Just prepare for it. Okay. Okay, so number 4, remember how we were talking about how the amount of moles is really important. The amount of strong base that we add to weak acid or strong acid that we add to weak base to create a buffer system, those amounts are really important. So I have these in molarity here. So we don't want to think about it in molarity. However, we have these in equal volumes. So that means we can just convert these. I won't write them all out, but 2 molarity will equal to 2 moles, basically, since they're all equal volumes. So that's one way to think about it. So you don't need to worry about converting them to moles because what you see is what you get, basically. So let's look at the first one. Well, first, let me remind you what we ideally want, right? When we want to find that buffer system, we want those conjugates to be around. Therefore, we want more weak species than strong species. Like we want 2 molar of, let's say, HF and 1 molar of NaOH. We want more of the weak one than the strong one. Otherwise, it won't create a buffer system. And we saw that many times. Okay. And I can clarify that again if anybody needs, which is no problem at all. So in this case, this is awesome, right? This is just what I wrote down. We have more of our weak species than our strong one. And so this will react together and they will form a buffer system. They'll form some F minus for us, and that will create one mole of HF and 1 mole of F minus. Okay, the next one, this is also a buffer system. We have conjugates here, right? This is the definition of a buffer, so that's all good. And then for the next one, so you'll cross this off, this will be an acidic salt, and then you have NaOH. So they can react, but notice the concentrations here, or the moles, right? They're the same. So what you're going to get is all of it will be consumed. All of the acidic salt will be turned into its conjugate base. I have questions. Does it matter that HCN and NaCN are the same concentration? Well, the reason we don't want this acidic salt to be the same concentration as this strong base is because they'll both react and turn into the conjugate base. Okay, so I can actually show you what's going on. So we'll have, actually don't want to write that all out. Okay, so that's going to be an acid. So we'll just say HA plus OH will turn into A minus, okay? If we have 2 of this and 2 of that, then these will both be subtracted. This is the strong base, and this is the weak acid. And I'm talking about number C here. These will both turn to 0, and this will turn into 2, right? I wrote that really weird, but okay. So the reason that C is not a buffer is because this weak acid reacted with this strong base to form only the conjugate, okay? Only the conjugate, all right? We have no acid left over, 0, right? We only have the conjugate base. Okay, so then why is B correct? Okay, why is B correct? Let's write that out. Because HCN is not going to react with NaCN, that's why. So NaCN, I'm going to simplify, just CN minus, right? And what would this be, like H3, H plus, okay. We don't really care about this right now. We just care about our buffer system, right? So for B, it's saying we have 2 of this and 2 of this, okay? That, we already have a buffer system now. That's it, we don't need to worry about anything else. Okay, and let me read all the things in the chat. Okay, so hopefully that clears up why B is a buffer system, because this is the definition of a buffer when we have the 2 conjugates both in solution, okay? They could be the same concentration, they could be different concentrations, it doesn't matter. This was always our goal, to have our conjugates both in solution. So let me start answering some questions. If the concentration of acid and conjugate base are equal, won't they cancel out in... So they won't cancel out. What's going to happen? That's a great question. I don't know if it's going to be pertaining to this quiz, but it definitely will on the next quiz. Okay, let's say we do have the situation in B, okay? So in the Henderson-Hasselbalch equation, this is what we're going to have, okay? So the pKa of HCN is around 9. We're going to have a log of 2 over 2, okay? What does this equal? What does this equal? This equals 0, okay? Because anytime we do log of 1, because this is 2 over 2 is 1, and anytime we do the log of 1, we'll get 0, okay? So we're going to have pH equals 9 plus 0. What does this mean? What does this mean? This means that the pH is equal to the pKa, right? Because this is the pKa, or when concentrations of HCN equal CN minus, okay? So this is the midpoint, which you probably learned about. Okay, so I have a lot of questions in the chat. Hopefully that answered that question. If you only worry about the moles when you need to have a strong acid, okay, I'm not sure. So if it's a weak acid and it's conjugate base, the concentrations don't matter because they're both present. That was always the goal, is just to have them present in solution. How do you know it reacts with water and not the CN? Yeah, because, yeah, Jerry answered that. Okay, great. Perfect, thank you, Jerry. Beautiful answer. Okay, so that's this question. Any more questions? You guys had we had a great conversation about that. Okay, otherwise I will go to the next question. These are the only 2 answers, but I can go over the other ones. So for D, we had more HBr. Oh wait, sorry. We actually just had HBr and NaOH. So those are both strong acid, strong base. That's not going to create a buffer system. E, we have an acidic salt with a neutral species, and that's not going to create a buffer system either. So those are A and B are the only 2 answers for that one. Okay. So we can kind of jump to number 5. So for these, the way you want to approach these problems is find the pKa for all of them, okay? So the pKa for HF is around 3.14. This is supposed to be HCN. This is going to be around 9. And this is not going to have it, or neither is this. And this is going to be a buffer system as well, which you'll need to find the pKa for. which I do not have, but you can calculate the pKa for all of these. However, I already found my answer right here, right? Because this one buffers around 9. Buffers will buffer around their pKa, okay? So you want to always look at pKa's for this problem. Yeah, so hopefully that makes sense. The last option, I believe this is a strong base anyway, so that's not going to work. Yeah. Any questions on this one? How did you find pKa? pKa is negative log of the Ka. So if you take the Ka of HCN, you'll do negative log, I believe it's 6.2 E negative 10, and you will get like around 9. And that'll be your answer here, because we're looking for something around 9. Hopefully that makes sense. So do you find the pKa of the strong acid? You guys are never told the pKa's of strong acids because they're super high. They could be like 60. You know how we're dealing with things like 10 to the negative 10 power? No, like strong acids are like really high. They're like 60, 40, 30 pKa's. So no, you won't be dealing with strong acid pKa's. Is D a buffer? It should be. Yeah, it is, yeah. You can calculate pKa. I don't think I did, but I can calculate it for you if you'd like, but it is not the answer. Which one is that? HC3. Okay, well, you understand the point, hopefully. I think it's, I might have made a typo on that one, but anyway, regardless. Okay, no matter what, you'll be given the Ka's and KV's for everything. Like even if it's not on your Ka table, it'll be given in the problem. Okay, so you'll never be helpless. Don't worry about that. Yeah. Okay, as long as you understand the point, though, hopefully, that is what is important here. Just look for the pKa and then have it match the pH. Okay. So next problem. Calculate pH of a solution that is 0.75 molar of HF and KF. Okay, so first thing I see here, I see buffer solution, right? That should be sounding alarms. Buffer system, the only thing I think of, the only equation I know is the Henderson-Hasselbalch equation, right? So what is the pH? So we're looking for pH equals pKa plus log of, this is going to be, this KF is basically just F minus. And so we're going to do 0.89, so deprotonated form, or the conjugate base over the protonated form, aka the acid, so 0.75. And when you put that all together, you should get 3.2, I think it's a 1, 3.21. Part D is polyprotic. Yeah, I thought so. So I definitely made a typo on that one, but it's okay. Yeah, I will fix it. Yeah, I thought there would be 2 hydrogens there. Anyway, okay. Any questions on this one? Using the Henderson-Hasselbalch equation, finding the pH. I wanted to do a question on, I forgot to actually like do it to like send it off, but I had a question on like the review session, basically asking like, what are the 3 things you can find from the Henderson-Hasselbalch equation? Those 3 things are, number 1, the pH, which we did in this problem. You can also find the pKa, and number 3, the ratio of deprotonated over protonated, or maybe another option would be if you're solving for, let's say, if you don't know what the initial value is, let's say, don't no initial concentration of your acid, let's say. So acid concentration, you can do something like, I'd have to kind of write it out, but you can basically use this situation here to solve. I can give you an example because that might be important. Okay, let's say you have a pH of like pH equals 2. Let's actually make that higher. And your pKa is going to be the same. It's going to be 3.14. And you don't know what your concentration of HF is. So you'll set that up. You'll do HF plus H2O turns into F minus plus H3O plus. Okay. So you know what your pH is, right? So you can find a lot of things from the information I just gave you, okay? First of all, you can find the Ka value from here. From this one, you can find the H plus concentration at the end. So that'll be over here. Final, after the change. You don't know what this is, so this can be question mark. Okay. But we're gonna have some change, right? All right, so if you see where I'm going here, you know what the H plus concentration is, okay? So that, we went from 0 to this H plus concentration, which I can calculate really quickly. Just by doing 10 to the negative 4, because our pH is 4. I'll actually write in numbers because it's probably easier to understand. So we'll do 1e negative 4. The only way we can get from 0 to 1e negative 4 is from adding that number. So we know our change is 1e negative 4. And we're going to apply that everywhere, right? Including on the left side, right? Okay. And then we can do that over here. Usually you'll be dealing with moles. And so with moles, usually you do not apply the 5% rule, okay? So we're gonna leave this alone. We're not gonna simplify it. You'll get like the Ka, which actually you should have the Ka for HF anyway. But you'll get the Ka, and you can set that equal to, the Ka, like 1e negative 4 squared over your question mark minus 1e negative 4. That's one way to do it. Another way you might run into is if you're given the pH equals 4 equals 3.14. So this is your given pH equals your pKa, which you know, plus log of your deprotonated form, 1e negative 4 over question mark minus 1e negative 4. Okay, and then you can solve for question mark that way, which is a really common problem that you'll see. Yeah, and you can put in here, you can put moles, you can put molarity. It doesn't matter because it's a ratio based, and so you'll get the same answer. Okay, just wanted to clarify that. Any questions? And I'm going to move on to the next problem otherwise. So for number 7, let's see, calculate how many moles of NaCN are needed to create a 1 liter solution. We're only dealing with NaCN here, just to clarify, at a pH of 10.67. Okay. So the first thing I want to do is find the concentration of OH. Okay, why do I want to find the concentration of OH instead of H plus? Well, this is a base, right? So this NaCN is equivalent to CN minus. Okay, this is a base, weak base. basic salts, same thing. So let's write out our ice table and kind of work out what's going on. So we have CN minus plus H2O turns into HCN plus OH minus, okay? And we can actually derive a lot of information from this number here, 10 to negative 10.76, sorry. I'm sorry, give me 1 second. Sorry about that. Okay. All right, so we can tell a lot. We can tell a lot from that pH, right? We can find the concentration of OH. But the first thing we need to do is 14 minus 10.76, right? Because we're looking for OH, we're looking for POH, right? So let's do that. 14 minus 10.76, okay. 3.24. That is our POH. We want to find the OH concentration. We just do 10 to the negative power of that. Okay. That will equal 5.75 E negative 4, which is our OH concentration. Okay, great. Now we can do a lot more now. I'm going to move this over. Over here. Okay. So we know our final concentration of OH is going to go over here. Okay. We started with 0. We started with 0 plus x plus x. So we know this x value. The only way to get from 0 to 5.75 e negative 4 is by adding that exact number. So instead of x, I'm gonna write what I found out here. Okay. So let's see what's going on the other side. We don't know what the initial is, right? That is actually what we're looking for. We're looking for how much of it did we even need to add to get our final pH, right? Okay, so we know we're going to be subtracting this amount, 5.75 e negative 4. Okay, so this is our setup, great. Now we can just use the Ka value, which is 6.2. Do products over reactants. Over x minus 5.75 e negative 4. And we just do some algebra, and eventually we will get our answer. Oh my God, you guys are so great. I'm so proud of you guys. You caught it. Okay. Yes, you're not supposed to use the Ka. We're supposed to use the Kv. And I'm so proud of you guys. Okay, I had a question. Where did I get the 5.75 e negative 4 from? That's just over here, Cam. This is over here. So I found the POH, which is over here. I did 10 to the negative power of the POH so I can find the OH concentration and then put it over here, okay? Hopefully that makes sense. All right, so thank you guys so much for realizing, yes, you're supposed to use the KB and not the Ka. Thanks, guys, you guys are awesome. So you just do, I should have written that down. 1 e negative 14 divided by 6.2 e negative 10. 1.61 e negative 5. This is why you guys need to like triple check your answers before submitting them. Do you not use the 5% rule in this situation? I don't think it should affect the number too much, honestly. You probably could, but just in case I'm not, it probably will not affect the number at all. I don't think it will. Okay. So, well, actually, it won't. It'll affect it by this amount. It'll affect it by 0.000575. That's how much it'll affect it, and that's not much at all. So if you want to simplify your math, yeah, you can just remove it. Okay, and then you'll solve for x, and you should get 0.0206 molarity. Okay, so that's not what the question was asking, right? The question was asking how many moles. Okay, but thankfully this was an easy problem because I only put 1 liter in there. Okay, so all you would need to do is multiply this by 1 liter to get moles, and that is the same number. So if it was not 1 liter, you would have to take care of that and calculate the number of moles. But yeah, any questions? Any questions on that one? Okay, so this is the final answer. All right, next problem, ranking. Okay, great. Sorry. So first thing I'm gonna do, I'm gonna label what everything is, then I'm gonna separate them, right? I'm gonna divide them up and separate them, okay? So first one is gonna be a strong base. Next one, strong acid. Next one, weak acid. Next one, acidic salt. Next one is basic salt. Next one, basic salt. Next one, basic salt again. This one, acidic salt. Okay. So now first thing I'm gonna do, I'm gonna separate them and put them in different categories, okay? So we already know HNO3 is gonna be the most acidic one, put it at the top. And I already know KOH is gonna be the most basic one. So my order is kind of going like this in terms of acidity. But first, I'm not gonna put them in order because I don't know which one's which yet. So I'm just gonna put them in their respective sides. So HF belongs on the acidic side. We have our acidic salt here, so C5H5 and HBr. I have my basic ones, Na. Okay. All right, so we have these. The next thing I'm going to want to do is compare their Ka values if they're on the acidic side, and then Kb values if they're on the basic side, okay? That is how you do these. So in this problem, we don't have any neutral species. If there was a neutral one, you just put it in its own category. It's going to be between acids and bases. You'll usually only get one neutral one. I think you'll exclusively only get one neutral one in every problem you'll ever see. But anyway, okay. So we know this one's going to be number 1. This one's going to be number 8. And then what's happening in the middle. So basically, you'll need to do what you'll need to do. And I won't write all of them out now because it'll take literally like 15 minutes for me to write out all the Ks and Kbs. But you don't need to do that for this problem. I know it's say like rank, but all you need to do is identify the third most acidic. So you already know, okay, we have 4 acids here. You already know that none of these are going to be the third most acidic, right? Because they're all on the basic side. We already have 4 contestants here ready to be in the top 4, so most acidic. So we know none of the bases are going to be the answer. I could rank all of these for fun, and I can show you the actual ranking of them, of all of them. But I'm going to tell you right now, you don't need to do all of them, and you shouldn't be doing all of them on the quiz if it only asks you to find like the third most, fourth most, second most acidic, whatever it is. Okay, so you'll just rank them by Ka values if they're on the acidic side, right? So This will be 7.2 E negative 4. This one you'll have to convert the KB into KA. Let me see. Once you do that, you should get, oh my God, it's so small. 5.88 E negative 6. And then for this one, you'll again have to convert the KB to KA, and you should get 5.5 E negative 10. Yeah. And so then we can like put these in order. I'll put these in order for you guys, so it makes sense. Actually, they're already in order. Okay. So that's number 1. This is going to be number 2. This will be number 3. This will be number 4. They're in order of their KAs, okay? Isn't the KB, yeah, that's a great question, Dana, but we're looking at the KB or KAs, right? So we want to convert the KB, we want to convert it to the KA, and this is my KA value over here. These are my KA values. Yeah. So we do not want to compare KBs when we're talking about acids, okay? It's on the acid side. We only look at KBs when it's on the basic side. So over here, you'll notice KCN, that has a KA on your KA table, right? But you need to convert it to its KB to properly compare apples to apples, pears to pears, oranges to oranges, whatever it is, you know? Okay, great. So we know the answer because we're looking for the third most acidic is going to be this one. I'm going to write out the order for all of them in case you did that and wanted to know. So this is the correct order. So we have 1, 2, 3, 4. And then on the right side, I'll write down the order. So I'm going to move these around so I can properly order them. Okay, so that's the order. This will be 5, 6, 7, 8. Okay. Any more questions on this one? Okay. I think this is the last problem. Awesome. Okay. Last problem, you guys. I'm so happy. A lot of you guys are sticking around. You guys are fighters. Okay. Let's do this. So basically, again, one second. Oh, you're looking for the answer, Megan? Oh, yeah. So the answer, if you really want to quickly know before you go, I will be emailing everything out anyway. But if you want to know, it is E. It is E. Could you see the answer for 8? Yeah, go ahead here. No problem. Okay, so let's break this down. Why is this E? So basically, my reasoning. So I'm going to write out kind of like a schematic, and so you kind of understand how to use the KAs, how to use them. This will be H2 minus, and then lastly, okay. The first thing I want to do is convert all the KAs to pKas, okay? So when you do that, sorry, I have it written down. Okay. Here it will be where the KAs lie. So the pKa here will equal 2.26. The pKa here will be 6.78. And the pKa here will be 11.29, okay? So basically, we're asking ourselves, what position do we want to be on the scale? Basically, it's kind of like a scale. So we can get a pH of 7.5, okay? On this scale, it looks like 7.5 is going to be around, somewhere here. So basically, what we want is, it's going to be somewhere between these two pKas. And so what we want is, we want to have, well, more importantly, it's It's between here. But just to kind of hone in on what we're looking at, I'm going to kind of erase the rest. That's not important because these are completely out of range, right? So this is what we're looking at here, okay? We want a pH of 7.5, okay? These are the only two species we're dealing with. They're in our buffer range we're looking for. And so we know it's going to be a little bit more basic than our pKa, and so therefore we're gonna have slightly excess of the basic one, okay? Because the scale is going that way a little bit. So that is why we have H2A minus, H2A minus, HA2 minus, HA2 minus with HA2 minus in excess, okay? A little bit more of it to make it a little bit more basic. But yeah, any questions? That